This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Hello everyone. Are there any people who weren't here, didn't come to the morning lecture? Sorry? Oh, really? So anyone here but not in the morning? All right, so not many. So I'm leaving these things here. So before you go or in the break, just grab one paper. All right, so we are talking now about rotation matrices. It will be a bit dense lecture, double lecture, and you have a lot of time to practice in the tutorial and then the workshop after that. So first, I'll be talking a bit about some motivation. Why do we need rotation matrices in this subject, right? And then I will explain to you about the notation that I'm using, and I'll give you a quick example for you to understand roughly what we are going to do with rotation matrices. And then we will go deep into the theory of how to construct a rotation matrix. Okay, and that will take most of the first and a bit of the second lecture. And then after that, I'm going to talk about common XYZ rotations, and we'll look through a few examples, right? So feel free to stop me anytime I'm talking something that you don't understand. Stop me, yeah?
Your microphone doesn't work.
At all? I can hear that. One. Okay, I just need to swallow it, right? Okay. I'll try to hold it here, but if you all are quiet, you will be able to hear me. I'll put the volume as high as I can, which is that. Okay, I'll make my most attempts to shout, okay? All right, so what I have here is some rotating objects that you can view their rotation, okay? Now, you can imagine someone trying to program these objects moving. How would they plot that? They will not probably redraw every time from scratch. You can imagine them kind of mapping, let's say the Earth, mapping it once on some coordinate system that is, you can imagine as attached to that Earth, okay, and then having some way to map between one coordinate system that is fixed, okay, and the one that is attached to this Earth, okay, some kind of mapping or a way to transition between coordinates on the coordinate system that is rotating with this Earth to a fixed one from where you are observing, okay? Not drawing every time from scratch a different view, okay? If it's not clear, that's fine. I'll come back to this. But you will be animating in the subject. So you can think about a very convenient tool that we are going to have attaching coordinate systems to different moving objects, drawing these objects kind of simply in those coordinate systems and then transitioning from a moving one to a non-moving one in some systematic manner. Okay, here is maybe another example that you can imagine the use of what I'm talking about. I have here a robot, and its end effector has, let's say it can have a camera or something like that, and the robot communicates with the world via its yellow end effector coordinate system that I named R, coordinate system R for robot. All right, this robot frame in curly brackets. Okay, R would stand for robot frame, and the table has its own separate coordinate system. By the way, I use frame as frame of reference and coordinate system interchangeably. That's the same thing. All right, so the table has this blue coordinate system attached to it, doesn't move, whereas the robot one can move as the robot manipulates an object, let's say. And we need to specify, let's say, program to the robot, can you please grab this object and do something to that object, place it somewhere else. And as we program, we want to be able to say this, the location of this object is so and so, right? And it will be convenient for us to work in the table frame, to specify all the numbers in the table frame, which is so stationary and nice, right? But as the robot moves, all the joints change their configurations. So the robot kind of understands things via the yellow robot frame. And you need to be able to calculate what is the position of the object in the robot frame if you know what is the position of the object in the table frame. Okay, so this transition will be allowed mathematically once we start working with rotation matrices. That's not the only way, but it's a very convenient way. Okay, very straightforward. And you can think of that in a way as a dictionary between different languages, but instead of different languages, you have different coordinate systems, different representations of vectors. Okay? All right, so let's look at my notation. Okay, I will be pumping this notation into you today. Hopefully you can remember. So rotation matrix we will denote by this R. Now, this R is bold and non-italic. Okay? A vector would be bold but italic. Okay? A matrix will be in the subject, bold and non-italic. And the scalar would be not bold. All right? So I have two letters here. At the bottom, is the coordinate system from where I'm transitioning, and the top one is to where. Okay, so I would pronounce that rotation matrix from R to T, or from the robot frame to the table frame. Okay, and we can have their numbers and various things, which are essentially the labels of the frames we are trying to set that dictionary for. Okay, so this would be like the dictionary from, say, Russian to Turkish, and this from Turkish to Russian. All right? They are doing the opposite thing. Okay, so this is to stand for rotation matrix from T to R, from frame T to frame R. All right? In terms of my notation. And what would we use it for? Well, briefly, if I would multiply this rotation matrix with a vector in frame R, the resulting vector would be in frame T. Okay? So this is the algebraic operation of this rotation matrix. Okay? And this is a 3x3 matrix. And we will learn today what are the entries of that matrix given two coordinate systems. Okay? So here is the simple example to just motivate what we are going to do. Now imagine you have the robot kind of here, and you know, or let's say the robot senses the corner of the table at this point OT, and it knows how to generate this red vector from the, let's say, the end effector of the robot, okay, OR, to point OT, which is the corner of the table. Let's say origin of this table frame. Okay, and let's say it knows how to calculate that with respect to itself, the robot. All right, so I would write here little r here, r to stand for robot frame. So it means that the coordinates, the x, y, z coordinates that I write here are projections onto the x, y, z axis of the robot frame. Okay, this will be a bit clearer later. And at the top here, you have the little t at the top left of the vector, position vector r. That one means that the entries x, p, t, y, p, t, z, p, t are measured along the axis of the table frame, okay, the blue one. So these are projections of this vector, the green vector, from the origin of the table, let's say the corner of the table, until this object or point P. Okay, so I will go one step back and say every vector could be represented or written in any coordinate system. And every different representation would have different kind of x, y, z projections corresponding to it. For example, if I have a word, I can say that word in every language. It would sound differently, but the meaning would be the same, right? So the rotation matrices are like the dictionaries to transition between these words, right? If I want to say hello in English, if I want to say, what do you say, like ni hao, I think. In Hebrew, we say shalom, salam. These are all different representations of the same meaning. Okay, so similarly, I can represent a vector in different coordinate systems. Okay, this is what we are looking at. All right. So the task, like for this example, is to find the purple vector from the robot and the vector to that point P. So if the robot wants to grab the object, it needs to calculate where to go. And I programmed the location of the object in the table coordinate system, how to find this purple vector in the robot coordinate system. So what I need to do, I would sum the two vectors, the red and the green. I would sum them. Sorry, I think I should be using my pointer. So I would sum these two vectors, right? But in order to mathematically combine the x, y, z components of each, I need the two vectors to be in the same coordinate system. Otherwise, I'm summing apples and oranges, right? So what do I want to do? If I want to get the result in the robot frame, this R, this one is already in the robot frame the way it was kind of given in this example problem. And this one, this vector, was given in the table frame. So I will need to use the rotation matrix from the table to the robot frame to convert this green, this given vector from OT to P in the table frame to the robot frame. Okay, so I would need to do this multiplication, and then I can sum. All right, and whatever the result is, sum 3 by 1 vector, that would be the purple vector represented in the robot frame. Okay, so what we are doing in this lecture is finding systematic way to calculate these A, B, C, D, E, F components of a rotation matrix if we know the orientations of the two frames between which we convert. Okay, so if we know exactly the orientation of one frame relative to another, we will be able to calculate the entries of this matrix. Okay, so this is the overall picture, okay, of what we are doing. Is that roughly clear? Roughly? Yes, I hope you are not too overwhelmed. Any questions? Yes?
Since we're putting the T showing that this is in the table's frame, why do we have to say that R is the position from the origin of T to P? Couldn't we just delete the origin?
No, we will be working in this subject with what I call free vectors. So these vectors are not really starting from a given point. So I could also represent the vector from starting from OR going to P. I can represent it in the table frame as well, right? And not only position vectors I will be working with, also velocity, acceleration, forces. Let's say force, there is no start point, really. So all the vectors are going to be free vectors, and I will always, if I want to say direction and size, I can do that. If I want to specify like a start and end point, that will be an equivalent thing. Yeah, so I don't assume what you said here. If you go into robotics, you will do something like you said, like, yeah, but in general, every position vector I would specify from where to where, not assuming any origin. Okay, so what we are going to do to be able to systematically find the values of a rotation matrix, how to calculate it in general, there is a recipe, okay? And I'm going to derive this strategy, but in order for this to make sense to you, first I'm going to work on a 2D example, and then from the 2D example, I'm going to generalize it to a 3D framework. All right? So for the 2D example, let's see. Okay, now I can't do everything. I mean, I need to have both my hands. So try to listen to my voice without the mic really attached, all right? Okay, so in this example, I'm going to have two coordinate systems in 2D. Okay, it's a very simple example. So let's say these two axes correspond to x A and y A. Okay, so I'm having some frame A like that. Where is ZA? Coming out, remember, from the morning. Okay, and now let's say I'm having a frame B, or coordinate system B, like this, in a different orientation. So, and this one is XB and YB. And let's say that the relative angle between them is, let's say, theta, okay? And I also have a vector, just some random vector, let's say vector V. Now, this hat stands for a unit vector. So these are all with dimension 1, magnitude 1. But the green one has an arrow on top. It could be a non-unit vector. And what we can do is represent this general vector V. I should also add here another coordinate system B. We can represent this vector V either in frame A or in frame B, right? So in order to represent it in frame A, I need to draw these projections on the axis of frame A. Okay, and let me call that, let's say, Vxa and Vya as the scalar numbers, the values of the shadow of this vector V on axis XA, on axis YA. Okay? Or alternatively, I can project this same vector V onto the axis of frame B. So that, let's say this is Vxb and Vyb. Okay? So, what do I mean by represent? If I want to write the vector V in frame A, I would write the A label at the top left here, and I would write it like that, as Vxa, Vya here, and 0 projection on the ZA axis. All right? If I want to represent the same vector V in frame B, the the coordinates or components would be vxb, vyb, and 0. Okay, so excuse me for the non-straight, that should be 90 degrees. Okay, so what I just did here is the two steps, 1 and 2, representing a general vector in frame A and frame B. All right? So what is step 3, representing the axis of frame B in frame A? What I can do is look at this axis, xb. Yeah? It is a vector itself. Okay? It has magnitude 1 and some direction. If I write this xb in frame B, it is just the very simple 1, 0, 0. Right? And YB in frame B is what? Right, 0, 1, 0. Okay, now if I want to represent XB and YB in frame A, I would need to project, say, XB onto the axis of frame A and project YB onto the axis of frame A, right? Sorry? So what I'm going to use, let's think about the projections. What is the projection of XB onto XA? Cosine theta, right? All agree? Right, cosine theta. And onto YA, sine theta. And onto ZA, 0. Right. And how about YB projected onto the axis of frame A? How do I represent YB in frame A? Minus sine theta. That would be the projection. Yeah, sorry? Cosine theta and 0, right? So this is step 3, representing the axis of frame B in frame A. Right? And now, what is it good for? What I can do, if I want to write a vector V, I can write, let's say if I write vector V in frame A, I can have like a superposition of the components times the unit vectors. So I can write it as Vxa times, times 1, 0, 0 plus Vya times 0, 1, 0 plus 0 times 0, 0, 1, right? Where this is XA, YA, and ZA all represented in frame A, right? Which means in order to construct this vector, I can go like that here, plus like that upwards, right? Like this. But I can also go like this and like that, right? But if I go this way, I can still use the representation in frame A. Why? Because I already obtained this direction and this direction in frame A. Here. So I can also do V in frame A as that amount, which is Vxb times the direction of xb, so xb in frame A plus that amount Vyb in this direction, Yb expressed in frame A. So all the vectors here are expressed in frame A, okay? And these scalars just tell me how much to proceed in a given direction, okay? So if I would substitute that, I would substitute the xb and yb that I received here. Okay, what would I get? I get Vxb times cosine theta sine theta 0 plus Vyb times minus sine theta cosine theta 0, and I can do plus 0 times 0, 0, 1, which is the ZB projected onto the axis of frame A, because ZB and ZA are parallel. All right. What I did now is this step 4, substituting the result from step 3 into step 2. Kind of. Okay, so I looked at these directions, xb and yb, but I represented everything in frame A. Okay. What I'm going to do now is to equate this right-hand side to the representation of V in frame A, the original one, this one. It's equal to Vxa, Vya, and 0. Okay, so I'm going to write it as equal to Vxa, Vya, 0. Okay, that equal to that. This is step 5. And step 6, extracting the resulting rotation matrix, would be to just write this part in a matrix times vector multiplication form. So we can write it as this. I can write it like that. So here I'll have cosine theta sine theta 0 minus sine theta cosine theta 0, 0, 0, 1. And here Vxb, Vyb, and 0. Okay, so you can check that this corresponds to that. Yes? Where these came from? This one? So if you look at this, go back here, I equated it to V, the vector V represented in frame A, and this is what I wrote here. This is my V in frame A, which is this and this. Yeah? So this and this. Okay. And what we are having here is the rotation matrix from frame B to frame A, Why? Because if I multiply a vector, this is the vector v, expressed in frame B, I will receive the same vector v in frame A. Okay, so this was a 2D simple illustration. What we are going to do now is to generalize it to 3D. Okay? Are you with me still? All right, so I did this example. It took me some time, and now hopefully I can go a bit faster, because in previous years I didn't do that at all. Okay. So I'm just going to, for the sake of lecture capture, I'm going to change the screens. Okay. Okay, so what we are doing now is the 3D case. Steps 1 and 2 were just to write the vector v in the different coordinate systems. So this is what I'm doing here, all right? Now instead of writing vxa, vya, vza, I just write here xa, ya, za, which might be a little bit confusing for you. Notice how this x is not bold, whereas this x is bold, okay? Because this one is a vector. It is the unit vector, which is the axis x of frame A, okay? And this is the amount by which I need to proceed along this axis, okay, as I'm constructing my vector v in frame A. Okay, so v is that green general vector, all right? So this is a superposition of component times 1, 0, 0 plus component times 0, 1, 0 plus z component times 0, 0, 1. All right? Similarly, I can do the same in frame B, which is oriented differently, right? What's the next step? The next step is representing the axis of frame B in frame A, right? This is what we did here, right? This step. So I'm taking, say, XB, YB, and also I need to do the ZB thing. Each of them I need to project onto the axis of frame A. Okay, so just to give you one example, I'm taking YB, projecting it onto XA, YA, and ZA. Okay, just for the example, but then I'll do it for all of the axes of frame B. Okay, so here I took the red YB, okay, and I check the components or the projections of this vector YB on the on frame A. Okay, so XA, YA, ZA. And what are these components? Just like we had here, say, cosine theta, sine theta, and 0, it was pretty simple. Here in 3D, we should have 3 angles. Okay, cosine of alpha would be the projection of YB on XA. Okay, if alpha is the angle between these two axes. Okay, maybe I'll just clarify that. If you are doing a projection, if you have some vector, let's say C, and another vector D, if you have this angle between them, let's say gamma. Yeah. Do you remember C scalar product with D or dot product? Giving you this size, the magnitude of C times magnitude of D times cosine angle between them. Okay, so if you have now unit vectors, if both of them are of size 1, magnitude 1, yeah, so let's say YB and XA, and this angle is alpha, okay, between them. So I will have this projection as cosine alpha, this one, which is 1 times cosine alpha, right? What I can do is say that YB dot XA, it is simply 1 times cosine alpha, right? So instead of writing cosine alpha, I could, if I wanted to, write the dot product of the different axes. That would just say, in other words, cosine of the angle between these axes. Okay? Because all of the axes of coordinate systems we are working with are unit vectors. Okay, so their magnitude is 1. All right, so this is why I can write here like a vector dot vector. Okay? So cosine alpha is essentially the value of cosine alpha is the projection of YB onto XA. And I can write it in an alternative way as YB dot XA. Okay? Now, in what coordinate system to take these two vectors? Either any coordinate system, as long as it's the same for both of these vectors. So I don't even bother writing any label on the top left. Okay? This just stands for cosine of the angle between these two axes. All right? Okay, so cosine beta is the projection of YB onto YA, and cosine gamma is the projection of YB onto ZA, right? And if I know the orientation of frame A and the orientation of frame B, I should know all of these alpha, beta, gamma angles, right? But now, in general, if this is just YB, and I need to do the same for XB and for ZB to get the rotation metrics, I will need 9 such angles, right? So it's a little bit confusing to remember alpha, beta, gamma, delta, epsilon, and so on. So instead of working with angles, I'm only going to keep this notation. Okay, so to do the same for XB, I'm going to say XB dot XA, XB dot YA, XB dot ZA. Okay, so this is what I'm doing next. What I'm summarizing here is on the right side, yeah, these are the projections of the axis of frame B onto axis of frame A. Okay, this is what we did here. Here we just did it for X and B, but I can also do it for Z. In this case, it's just 0, 0, 1. Why? Just because ZB and ZA are aligned. Okay? So these three things, in general, appear here. All right? So this is step 3. And what I have here is just a reminder of x being b is just saying 1, 0, 0, okay? YB in frame B, 0, 1, 0, and so on, okay? Who is with me? You're lost. Any questions? Can you at least see the similarity between what we are doing for 3D and what we did in 2D? I think you did follow my 2D example, right? Now, are you unhappy with this notation? Having like dot products inside vectors. Now, is that a happy or yes, unhappy? I will just remind you, this is a dot product. The result of that product is a scalar, right? Scalar, cosine of an angle, or let's say in here, say if I'm looking at xb dot xa, which would be this component, right? I'm doing 1 times cosine of the angle between them, xb and xa, which is just theta. All right? Oh. Okay, so this is one example. Here, another example. I would do here xb dot ya, which is 1 times cosine the angle between them. So what is the angle between xb and ya? If this is theta, then 90 minus theta, right? So 90 minus theta, and therefore I have sine theta. Okay? So the result of this is a scalar. Okay, so don't be afraid to look at this. Okay? This is just so that I don't carry cosine alpha, cosine beta, cosine gamma as before, because I will need 9 such angles and it will be a mess on a figure, right? So as you see something like this, it just means cosine of the angle between the two axes. All right? Cosine of the angle between the two axes. Okay? Now what is the next step? The next step was to represent to substitute in where was it? Here. So to write the vector v in frame A as a superposition of how much to go in the xb direction, yb direction, zb direction, and substitute the representations of xb, yb, zb in their A coordinate system. Okay, so essentially to substitute what we found here into this superposition. Okay? So if I do that, you can, so this is the original representation of the vector v in frame B, okay? xb, yb, zb. How I would construct this vector to go xb in the xb direction, okay, xb units in the xb direction plus yb units in the yb direction plus zb units in the zb direction. Okay, so now if I change the representation of all of these into their frame A representations, yeah, I'm also getting this V in frame A, because now I'm talking in terms of frame A components. Okay, just like here. Okay, this is the tricky part. Okay, but you can think about it. Okay, so this specifies how much to go in a given direction, and this is the direction. Okay, but that direction is a vector which I can represent in any frame, in particular in frame A. Okay, so this is what I did, plus go so-and-so in this direction, plus go so-and-so in this direction. So it's a summation of 3 vectors to arrive to the tip of the vector V, okay, from the tail to the head. Okay, does it make sense? Now I can substitute, instead of x be in A, y be in A, z be in A, I can substitute these. Okay? And as I do, it will look like this. And now the last step is to turn it into a matrix form. All right? Are you following so far? Okay? So the matrix form from here, like that. Okay? And this will be our rotation matrix from B to A. Why from B to A? If I would now multiply the vector V in frame A, represented or written in frame B, if I would multiply it by this matrix, I will get the result as the same vector V, but represented in frame A. Okay, so the components of the same vector, here they are in frame B, or components or projections into axis of frame B. Here they are projected onto axis of frame A. Okay? So I want to go back to my notation from B to A. When I say from B to A, I mean the algebraic transformation. As I multiply by this matrix from the left, I kind of go from B representation to A representation. Okay, so A is the result. Okay, remember again, from B to A means this algebraic function or algebraic equation. Why am I saying that? Because it doesn't correspond to any figure. I didn't draw any figure. Later on you will see some figures, some arrows going from axis of A to axis of B, and you'll be like, wait, but this axis goes from A to B. So go back to what I'm saying now. The terminology, the notation from B to A is corresponding to this algebraic equation. Okay? Converting from B to A. Is it clear? Okay. So now let's look. Let's look at this. It's time for the break, right? Yeah. Sorry. So let's have a break and resume in 10 minutes. Digest. What's the what? Reason? Why do we need rotation matrices? Because we will need to work with vectors in different coordinate systems. We would need... You will use it in real life. So what I was doing at the beginning, let's say here, you would attach one coordinate system to a moving object and another coordinate system to a, say, non-moving object, you need to transition between different orientations.
Can I ask a quick question? So as you mentioned from the 2D example, the VXA is the magnitude of the vector projected onto the A-axis, is that correct? So VXA
Yes.
is the magnitude of the vector projected onto the A-axis.
Yes.
So, but when you're doing the 3D example, this way, like,
Yeah.
so why
It's-
would you use the XB rather than,
Oh, this is what I did here,
yeah?
like here. I construct the
Okay.
vector bit by bit. So instead of going in this way, so as I construct vector v, I could either go this way
Yes.
or this way.
Okay. So why would you use one other than the other? So does it matter which one you use, or?
It doesn't matter, but I'm trying to
Okay.
make sense
Right,
of.
I think I get it here. So you're saying that these two equations, they are like equivalent, is that correct?
Yes.
These two
Yeah.
okay.
Yeah.
Okay, I understand now. Thank you.
So essentially in this equations that we're doing, are we simply trying to convert from one sort of coordination to another?
Yes. Yes.
Like a movement from, say, if my axis is initially like a normal XYZ axis, we're trying to rotate that
In another XYZ. Yes. Yes.
degrees at another
Yes.
different areas of XYZ.
Yes. Like here. Like here.
Okay.
You can have the same vector, let's say you have a vector v and two coordinate systems A and B, and they have different orientations. Yeah, so it will be really convenient to express vector v in, say, one of them, let's say B, if, let's say, this is parallel to this one.
Oh, okay.
Could be convenient, okay, but then later on, if we need to have v in A, we simply,
Just convert it.
yeah, just convert it by multiplying like this. So we need to find it.
Oh, so
Okay.
right now we're just trying to find the constant that we can use to work out.
Yeah, we are, I'm explaining how to construct this. Yeah, sorry. Yeah,
So do we actually start constructing the vectors? Do we like see the vectors first before we actually see the coordinate systems? Or do we see the coordinate systems first before we figure out where the vector is going?
You will primarily see the vectors and you will define your own coordinate systems for convenience. Yeah,
So if you want to say, if the vector v is going that way, we want to say, accept that as a vector of x of a, then we just convert it to v. It'll be way easier for us than we just
Yeah.
convert the vector.
yeah, and next week we'll do that.
Okay.
We'll assign coordinate systems to represent vectors in different frames. Yeah.
Thank you.
the vector stays in the same direction, same magnitude, but I would word it differently. What I'm doing is representing the vector in different coordinate systems. There are different ways to look at it. What you're saying, it's kind of what we are doing. I just don't want you to get confused between different ways to look at this problem. I will just kind of re-explain it quickly as I am starting. All right. Let me just recap a little bit the motivation behind what we are doing. We are going to work a lot with vectors in this semester, not just position vectors, could be angular velocities, okay, which are also vectors. And it will be really, really uncomfortable, inconvenient to work with a single coordinate system. So what we are going to do is assign different coordinate systems to our problem and define different vectors in different coordinate systems as convenient to us. Okay? But eventually we need to write down equations. And in a single equation, we want to have the left and right hand sides of the equation represented or expressed in the same coordinate system. So we want the ability to convert vectors from one coordinate system to another coordinate system. Okay, so I gave here an example to someone who asked me. Imagine you have some vector, okay, and you have two coordinate systems that are oriented in different ways, but you do know how one is oriented with respect to the other because you know the angles between the xyz of one to the xyz of another. If you find it convenient to express the vector in one coordinate system, we are asking ourselves here, how can we express the same vector in another coordinate system? Okay, so we need this dictionary, okay, which is in a form of rotation matrix, and this is what we are constructing here. We are constructing a rotation matrix that would do that job of translating the representation of a vector in one coordinate system to its representation in another coordinate system. Okay? This is the general motivation, and maybe today it's a bit shaky, but later on you will use it a million times, and it will be your second language. Vectors in different coordinate systems and rotating them, swapping from one representation to another. So we went through this analysis, let's say. I won't go through it again. Do have a look at it, a deep look at it to understand if you missed something, if something doesn't make sense. From now on, I will kind of practice that. All right? So in order to practice, I want to write down the rotation matrix for different cases, right? And in order to write down the rotation matrix, I want you to remember how to construct it from scratch. So how to construct the rotation matrix from frame B, some frame B, to some frame A, okay? And B and A could be like from frame 5 to frame 4 and things like that. So what would you do? You would construct this general arbitrary rotation matrix in a column way, column-wise. Okay? First column, second column, third column. What is the first column? That would be the projections of xb onto the axis of frame A. Okay? Second column, the projections of yb onto axis of frame A. Okay? I will try to keep B as red and A as blue for this lecture. Later on, we'll have different colors. Okay? Very colorful subject I have. And finally, last column, ZB projected onto the axis of frame A. Okay? Remember, say, this component, ZB dot YA, stands for cosine of the angle between these axes, ZB and YA. Okay? So every dot product is cosine of the angle between the two axes. Okay? Any questions so far? Okay, so what we are going to look at first are the 6 most used rotation matrices that are very convenient, and you will learn them by heart, for sure. Okay? So what I'm doing here, I'm drawing the plane, some kind of 2D plane, but I'm also adding, for your convenience, in the beginning, I will stop doing that later. I'm drawing the third axis that comes out of that plane. Okay, so our first 2 common rotation matrices are called or termed positive x and negative x rotation. Positive x rotation, negative x rotation. What do I mean by positive? Here, axis x, in both cases, axis x comes out of the plane. And here we have, if you follow with your eyes this arrow, yeah, this rotation, if you are using your right-hand rule again, if your thumb points in the same direction of x, that's a positive x rotation. Okay, whereas if your thumb points in the opposite direction of x, that's a negative x rotation. Okay, so essentially you need to apply the right-hand rule twice if you only see what's in the plane. Once to figure out where the axis that is not shown is going to. Is it out of the plane or into the plane? And then follow that rotation direction and see where your thumb points. Okay, if they are aligned with the third axis, then it's a positive rotation. Okay, not aligned, negative rotation. Don't be automatic on clockwise or counterclockwise. Okay, apply the right-hand rule from scratch every time. Okay, we will see that. So here I have this arrow kind of coming from the axis of frame A and ending at the axis of frame B, but I'm still calculating the rotation matrix from B to A. Okay, and why do I draw the arrows like that? This example will mostly correspond to having some object rotating, assigning or rotating about axis XA, and I want to assign a coordinate system that is attached to that object, and that would be B. Okay, and it would be convenient for me to represent vectors related to that object in frame B, because in frame B everything is kind of constant for that object because they are attached. Okay, and then I want to understand how to move from frame B to frame A with my representation of vectors. Okay, we will use it a lot, so you will see. But right now, I'm just following the rule that I told you, column by column. Okay, so let's look at, say, the first column. XB projected onto axis of frame A, okay, in the first case. XB dot XA is cosine of the angle between them, okay. Both are aligned. Angle between them is 0. Cosine 0 is 1. So I have 1, all right? Let's take another component. Let's take, say, this minus sine theta, okay? So ZB dot YA. ZB and YA. So what is the angle between these two? I have 90 plus theta, okay? So cosine of 90 plus theta, okay, it probably becomes minus sine theta, okay? You can calculate that, all right? And here, it is a similar case, okay? Would you be able to follow? Okay? You sure? Okay, so can you copy this drawing? Okay, because I'm going to hide it momentarily. Try to remember, or from your understanding, try to figure out, okay, rotation matrix from B to A. You have Y, A, and ZA, and YB, ZB. Oops. Now the x-axis, XA and XB, are both pointing outwards, right? Okay, so the projection of XB, the red XB, onto XA is 1, right? Cosine of 0. And because it is because XB is normal to both YA and ZA, normal meaning 90 degrees, cosine 90 is 0, this is just 0 and 0, right? So this is XB written in frame A, okay? What you need to put here and here is YB in frame A and ZB in frame A. Okay, so think about it and try to reproduce it. I'll give you 3-4 minutes. So try to work on it. Try not to look at the slides. I'll bring them back really soon. Okay, if you get a mistake, don't worry. Better you have the mistakes now, all right?
necessarily, it shouldn't have any like relation with the theta. It should be any value. You know what I mean? If you get back to the slide, I can show you.
I don't want to bring it up now.
Okay, so
But it doesn't matter from where I'm looking. I'm just measuring the angle between two axes. I have like two axes in space, and I measure the angle between them.
yeah, but doesn't necessarily have a relation between that angle and theta. If
I need to clearly define. Oh, here I have theta. I didn't wrote theta. This is theta. I need to clearly define the orientation.
It's the vector here. If the angle with this vector and this axis is,
still,
for example, phi or whatever.
Yeah, I
it
will
doesn't-
write cosine phi. Yeah.
Okay. Yeah.
Yeah.
But doesn't necessarily correlation between this axis, between this angle
And theta. Yeah, no.
Yep.
So what we are doing now is rotation that is easy to represent in 2D. It's only about, it's rotation about one axis such that we have the same x-axis of the two frames aligned, okay? It's a special case, okay? It's a special case. So I'll bring back the slide. Let's look. Okay. So this is your YB projected onto frame A. Okay. Why is it 0 cosine theta minus sine theta? Let's see. So YB dot XA. YB dot XA. XA and YB are normal to each other, right? So that's why we have the 0. Then YB dot YA. So YB dot YA. The angle between them is theta, so just cosine theta. Okay? I hope you got that fine. And YB projected on ZA, YB and ZA. Yes? Angle between them 90 plus theta. Okay, so cosine 90 plus theta would convert to minus sine theta. Okay? And similarly, this one. Okay, now try to do what I'm saying. Remember by heart. Okay? This, and this for the Y case, and this for the Z case, okay? All of these 6 matrices, remember them by heart, okay? Meaning and the form. Okay, so similar, very similar. We are having here positive rotation about Y and negative rotation about Y. Why is it negative rotation? If you follow with your hands, your thumb is opposite to the direction of Y. Okay, so negative Y in here, positive Y rotation here. Okay? So this is the case for Y. I'm not going to go here case by case, okay, column by column. I want you to have a look at that, okay? And this is the Z case. Does it remind you something? What we did at the start, right? What we essentially did at the start is a positive Z rotation, okay? So, again, please go through these 3 slides and memorize, but with understanding, memorize all the common 6 rotation matrices, which are about x, about y, about z, okay? Positive and negative. They are very similar. It's just a matter of where this minus goes, okay? Very similar, okay? It's really easy to remember, but please do that so that you can follow quickly, okay, later on. Any questions so far? Any questions, guys? Okay, so let me recap. So far we spoke about why we would need rotation matrices, okay, when we would need that, when we need to convert between representations of vectors from one frame to another frame. 2, how to construct a rotation matrix from scratch, why it works. We went through the mathematics of that. And 3, common rotation matrices, which are rotations about a single axis, either x, y, or z, and I told you please learn them by heart for your tutorial even, all right? So what we are going to go through now are some properties and some examples to practice, okay? And hopefully that would clarify everything you need for your tutorial next week. So the first property is the basic algebraic operation we are using rotation matrices for, which is the transformation from one representation to another representation. Okay, so this is what we learned so far. A vector represented in frame B pre-multiplied by the rotation matrix from B to A would result in the same vector but represented in frame A with its components written in frame A. Okay? So here you would plug in the components of the vector V in frame B, and you will get the result as the components of the vector V in frame A. This will be super, super useful. All right? You just need to find the rotation matrix from B to A to do that conversion for you. Okay? I have a few comments about this line. So my first comment is the vector V could be any type of vector, right? Any type of vector, position vector, velocity vector, acceleration vector, angular momentum, linear momentum vectors, moment vector, force vector, okay? Anything that is a 3x1 vector is pluggable into this formula, all right? In terms of notation, okay, do you understand now the label on the left? Yeah? So if I have this V and the label A next to it, it means that when I write the three components, the x, y, z components, I refer to the axis of frame A. All right? And the last comment is these two vectors, V in frame B and V in frame A, it is the same vector. So physically, it points in the same direction in space, okay? And it has the same magnitude. Okay, so if you look at the x, y, z components, if you take the square of all and sum them, it will be the same as summing the squares of all the components for this representation, okay? Because the magnitude is the same, okay? And the direction in space physically is also the same, okay? I can say, look at this vector, okay? And I can represent this vector in either this frame or that frame or that frame. Any representation will have 3 different components, but overall the direction and magnitude are the same. Okay? Just like hello means the same in all these different languages. Okay, the second property is the orthonormality. That means that rotation matrix, if you notice, we can look here. How do we construct it? This is essentially the vector xb in frame A, so xb, yb, and zb. xb, yb, and zb, they are all normal to each other, and they are unit vectors, right? So that's why this matrix is called orthonormal, okay? Because all the columns are normal to one another, and their magnitude is 1. And these matrices, they have a very cool property that their inverse is the same as their transpose, which means if we have the rotation matrix from A to B, we can get the one from B to A by simply transposing. Okay? Transpose the matrix, you get the inverse operation. Okay? So maybe to clarify, if you have R from B to A, and you have a vector in B to give you a vector in A, yeah, if you want the opposite action to go from A to B and get the vector here in B, this, how do you get it if you have this one? So this one is simply this one transpose, okay? Very simple. And then the next property of the cascading, it makes sense even from the first one. I just want you to notice how you can cancel diagonally like that, okay? So if you multiply several rotation matrices, you will always get another rotation matrix, okay? So you can multiply as many as you want. It will stay an orthonormal matrix with all the properties of a rotation matrix. So in this case, you have from D to C times from C to B times from B to A, and the result is from D to A. Okay, so this is convenient when you have lots of coordinate systems and you need to make all these calculations. Now, you can see already how you will have different sines and cosines flying around equations. That's why you will need MATLAB to do all these matrix products for you. Okay, you will end up having some long expressions, and MATLAB will be really useful and handy to calculate these big rotation matrices. Okay? So here is an example. I just keyed here some rotation matrix about x, positive rotation about x, positive rotation about y, and negative rotation about z. Okay, just for the sake of example. And I can multiply them. Here I have, say, C2 would mean cosine of some theta 2, for instance. Okay? And S1 would mean sine of theta 1. Okay, that's a convention that I invented for the code. Okay, you can use similar things to shrink the expressions. Okay, so as I evaluate this product, I'm going to receive the result of that overall rotation. Okay, now what we are going to do in this subject, because it is not convenient to jump from one totally arbitrary orientation to another, measuring all the 9 angles between the axes, we are going to use this property of cascading rotation matrices in a way that we separate rotations into rotation about one axis only at a time. Okay, so one axis rotation at a time. So you can look at this animation. Okay, you can think of a coordinate system attached to the red ring and one attached to the non-moving space. Okay, if you need to transition from these two, it would be a nightmare to jump straight away. So what you would do, you would assign some auxiliary coordinate systems, one attached to the yellow ring, one attached to the green ring, okay? And then you would go from one to another, each time only rotating about a single axis, okay? And this is a similar thing here. In order to represent a final orientation of an object, you would construct auxiliary rotations, okay? And you would have some convention in place. Let's say so-and-so degrees rotation about x, so-and-so degrees rotation about y, and then so-and-so rotation about z, okay? And then you would use 3 rotation matrices about x, about y, about z, and you know how to cascade them to get from the final orientation to the initial orientation, okay? So this is the idea overall, okay? We will use this idea, okay? I don't go too deep into it. If you look here, if you imagine that the initial orientation is kind of so in the initial orientation, this axis is x, this axis is y, and this axis is z. Okay, so first we have rotation about x, okay, if the top one is x, then some rotation about y, and then about negative z. Okay, so that's why I kind of pre-calculated with MATLAB. I can then cascade all these rotation matrices, positive rotation about x, positive rotation about y, and negative rotation about z. Okay, go to the references of all of the common rotation matrices I told you. And this is the result. This is the resulting matrix. Okay, you can just multiply them or use MATLAB for it. All right. By the way, C beta stands for cosine beta, and so on, okay? Now, what is this? This is a rotation matrix. From where to where? From the final coordinate system, which is the red one, I think. Yeah, the red one is the final one. So from the red coordinate system that is attached to the sphere, okay, it kind of moves with the sphere all the way, to the non-moving coordinate system, which is not drawn here. It is just the momentary blue one before it starts. So this is this rotation matrix, which is essentially from the sphere coordinate system to the stationary space. Okay? Now, if I want to know where this red axis points, this red axis is the z axis of the coordinate system attached to the sphere. I can just look at this last column, which is the z of the coordinate system attached to the sphere, okay, expressed in the, let's call it 0 coordinate system, okay, or the one that is not moving. A bit confusing, I know. Digest it a bit later. All right, do you have any questions so far? Do you understand something? maybe I'll just explain it a little bit again. Here, this rotation matrix, let's call it from 1 to 0, this from 2 to 1, and this from 3 to 2. Okay? So overall, we have here 3 to 2, 2 to 1, 1 to 0. So overall, this is 3 to 0. What is 3? 3 is the Z1. And what is 0? It is before it starts moving, the initial blue one, okay, the one that is fixed. Okay, every time we have just one rotation. First, you see rotation about x, if x is the top arrow, then some rotation about y, and then rotation about negative z. Okay. So this is the resulting rotation matrix from 3 to 0. And its columns are x3, y3, and z3, expressed in frame 0. Okay, so if I'm interested in a particular axis, I just go to the appropriate column in the rotation matrix. Okay? I will remind you that I'm constructing a rotation matrix column by column, okay? X, Y, and Z. Okay? Okay. So now let's do the examples. Okay, we have just the right time for examples. So take some time to think about this one. It's a simple one. Everything in one plane. What axes don't appear on that plane? XA and XB, where are they? How to determine? Right-hand rule, going from Y to Z. Y to Z, you get your X. From Z to X, you get your Y. So Y to Z, you get your X, which is inside. Okay, so is it one of the commonly used rotation matrices? Which one? Say again? Positive or negative? Negative. Why negative? If you follow the direction of rotation here, your thumb points in the opposite direction of the x-axis, okay? So it's a negative x rotation. So you can already use the rotation matrix here. Okay, copy it maybe if you like. So the equation you can write you can use this, by the way. You can use this property because you are looking here to find VB rather than VA. Okay, so it's kind of the opposite. I'll give you 2 more minutes to think, at least have an idea how to solve it. You don't need to give me the numbers, okay? Just a good idea, construct your equations. All right, let's have a look. So what you can, this solution that I'm presenting here is a bit convoluted, just like for beginners, okay? But later on, you'll do it very fast, okay? So this is the negative rotation about x. And you can construct this equation as this rotation matrix times the representation of the vector in frame B gives you the representation of the vector in frame A, which you know as given 0, 3, 2. Okay, so does this equation make sense? Guys, does it make sense? All right. So because we need to extract VB, we need to like pre-multiply the entire equation by the inverse of that. But we know the inverse of that is the transpose. Okay, so we can simply transpose that and multiply by V in A, okay, and that gives us V in B, okay? So this pre-multiplied by its own transpose will give you the identity matrix, all right? Because it's an orthonormal matrix, okay? Is it fine? Going to the next example, we have this case, okay? And you need to calculate the rotation matrix from frame B to frame A. Is it one of the commonly used rotation matrices? No. Why? We don't have a common axis like x and x pointing the same direction. Okay, what are the missing axes from this plane? We have YA and ZA, so where is XA? Into the page, okay, going from Y to Z. And we have XB and YB, where is ZB? Out. So they are in opposite directions, okay? How to construct the rotation matrix column by column. Okay, so attempt to project XB onto the axis of frame A. Then project YB onto the axis of frame A. And then project ZB onto the axis of frame A. Okay? So have a go. let's do maybe together one of the components, just so that if you are fine, keep doing. If you're lost, join me. Let's do, for instance, let's do this one. I don't know. I'm picking one randomly. So this one would be the angle between the cosine of the angle between ZB and ZA. Okay? Because I'm projecting ZB onto the XYZ axis of frame A. Okay? Now, in the drawing, where is ZA? There. Okay? Where is ZB? Normal to ZA, essentially, right? Because they are normal, it's cosine 90, so it should be 0, right? So this component will be 0, okay? Continue. All right, so let me review, okay? Whatever you manage to do, check, okay? This is the 0 that we got, all right? Whatever you manage, check. If correct, good. Incorrect, make the amendments, okay? Okay, so last example is this one, okay? Essentially, it's pretty much the same. What you just see here, a bit confusing, sorry, ignore this one. What you see here possibly confusing is that these coordinate systems are drawn without the same origin. And that's fine, because we are not going to care about where is the origin of any coordinate system. So in order to conveniently produce the rotation matrix and find the angles, you can simply copy one onto the other in a parallel fashion. Okay, so just copy. Okay, and then what is, say, the angle between x1 and y2? x1 and y2, the angle alpha. Okay, so cosine alpha would be the component in the middle column, first the top row. Okay, cosine alpha. Now, in order to quickly get that, yeah, what you can identify here, the z-axis come out of the page, right, for both of them. So z1 and z2 come out. So it's a kind of almost positive rotation about z. The only thing is it has an offset of 90 degrees. Why? Actually, minus 90 degrees. Because when alpha is 0, it's like I have an initial minus 90 degrees rotation about z. Okay, so I can simply plug alpha minus 90 into the positive rotation about z rotation matrix. Okay, now it might be a little bit hard for you to understand at this stage, and it's fine, just do the normal way, column by column. Okay, so you can check. Okay, so this is cosine alpha, as I mentioned before. Okay, I think we can finish for today. And let me know if you have any questions in all the means I told you. Thanks a lot, guys.
Sorry, I'm having difficulty comprehending just example 2.
Yes. This one.
So I was wondering,
Sorry, just a second.
the axes, I can't see the axes, how do I do it? So you said that this one is 0, so this is ZB and ZA, right?
Yeah.
So I have ZA here,
Yeah. And where is ZB?
so if it's like this, that'll be
X,
pointing
Y.
out, right?
Pointing out.
Yeah.
Yes.
So then,
So-
why is it 0?
Because what is the angle between ZB and ZA?
Oh, that angle,
Yes.
90?
Right.
Oh, so it's
Cosine
cos-
of 90.
Oh.
That's all.
Okay. I understand. Thank you. I'll try and figure out the rest.
I have a question about the next phase. Yeah. You mean the rotation matrix, but there is a movement of the.
Yeah. So just to produce the rotation matrix, ignore positions of origins. This is just drawn here for convenience and drawn here for convenience.
So in the actual questions,
You will draw that wherever you want. Yeah.
I got a question about the hand rule.
Yes.
So I thought this from other textbook. I just wonder by saying that when you are trying to figure out the direction of the x, y, and the axis of the coordinate, like beyond the rectangle, you can just do a straight.
Yes. Yes.
It really works, right?
X, Y, Z.
X, Y, Z, and it always works, right?
It's the same. It's just different technique. It's a different technique for the same thing. I use what I did in the morning. Did you come to the morning lecture? Yeah. So I don't like doing X, Y, Z because sometimes it's cumbersome for me to rotate my hand, and I also need to remember. Sorry, the mic. This one.
Thank you.
Do you want my key?
Yes.
Uh,
I'll be in the,
in my office?
I'll be in the lab.
Okay. Okay. Second.
Thank you. Cheers.
So,
Yeah, that's all
I
right.
have a little question. When you left, was it still recording?
No, not that big. Was it a big moment?